We've mastered the art of level flight and turns, but getting your wings means flying high, but sometimes also low. Planes are capable of flying at a wide range of altitudes, and in this lesson, we'll learn how to climb and how to descend, ensuring we'll get where we want to go at an altitude of our choosing. Welcome back to Navigraph Academy. This time, we're looking at how to execute coordinated and efficient climbs and descents in the Cessna 172. First, we'll look into how to counter the yaw effect and the pitch effect that results from increasing and decreasing the power, and these are called the slipstream effects. And secondly, we'll look at climbs. We'll discuss some of the important terms, such as the speed for best rate of climb, and show how we maneuver the aircraft to achieve this climb speed. Then we'll move on to descents. And first, we'll discuss power on descents, a condition where some of the engine power remains while the aircraft is descending. Then we'll cover the idle power descent mode, called the power off descent. This is our first interaction with the emergency procedures of the Cessna, as this descent procedure is also used when we're suffering from an engine failure. In order to climb and descend, we must first understand how the propeller affects the stability of the aircraft. And let us first consider the propeller's effect on the pitch stability of the aircraft. On a plane like the Cessna, the level flight pitch stability is achieved by a combination of forces generated by the wings and the stabilizer. The aircraft tends to rotate around the center of gravity, sitting about here. But since the center of lift acts aft of the center of gravity, the wings alone would generate a rotational movement, causing a pitch down force. And this alone would lead to an unstoppable nose-down tendency and a loss of stability. And to counter this, the aircraft has been fitted with a stabilizer. The stabilizer is an inverse miniature wing, and as airflow strikes the stabilizer, air is redirected upwards, which causes an aerodynamic reaction, in itself causing a downwards force. Since the stabilizer sits aft of the center of gravity, a rotational moment results around the CG, pulling the nose up. When we are in level flight, the wing, the stabilizer, and the elevator forces counter each other, and the pitch stability remains stable. As we change our power input, we change the balance of this relationship. And let me explain how this works. The propeller is essentially a large air shuffling machine. The more we increase our power, the more air is accelerated aft along the aircraft. This accelerated packet of air is called the prop wash, and the prop wash moves along the aircraft fuselage and eventually strikes the horizontal stabilizer. As this air is accelerated, containing more energy than the free-flowing air, it causes the horizontal stabilizer's force to increase. And this, in return, causes a rotational movement around the center of gravity, causing a pitch-up tendency. And the opposite is also true. If we reduce our power, we would feel a pitch-down tendency. There are more forces at play here, but the prop wash stabilizer interaction is the primary cause of the pitch on power reaction of the Cessna 172.
Let's have a look at this effect in the aircraft. Here we are, cruising in level flight. I'll smoothly add power without using any elevator input, like this. As you can see, the nose pitches up. If I want to maintain level flight, I must push my control device forwards. Inversely, if I reduce the power, our nose was going to pitch down. I will have to pull on my control device to maintain level flight.
The prop wash also creates another side effect. On the Cessna, the propeller is spinning clockwise as seen from the cockpit. And because of the rotation of the propeller induces a rotational moment into the accelerated air, which also starts a clockwise movement. This makes the prop wash spiral slightly as it moves along the body of the aircraft. The clockwise moving air strikes the vertical fin, causing an aerodynamic force that tends to push the tail to the right. In turn, this causes the nose to yaw to the left. And this left yawing tendency, as we increase power, is called the slipstream yaw effect, or simply the slipstream effect. To avoid fatigue by having to push rudder throughout the cruise segment, The aircraft is designed to have close to zero slipstream effect while it is flying in cruise flight. This means that if we increase power above the normal cruise power, we would have to push the right rudder. And if we go below the cruise power, we would have to push the left rudder.
It's easy to demonstrate the slipstream effect in the plane. As I slowly increase power like this, note how my nose will yaw slightly left. Let us go back to cruise power so that it can show how to counter the slipstream effect. As we'll increase power, we'll have to apply right rudder. To do this in a coordinated manner, I keep my eyes outside of the plane, fixed far on the horizon, and find a landmark straight ahead somewhere. Now I gently increase power, meeting with right rudder to keep my landmark fixed, unmoving on my screen. Inversely, when I reduce the power, I must use left rudder input. As I remove my power, I keep my eyes on the landmark ahead and use the left rudder input, like this. In the Cessna, the slipstream yaw effect is quite small, and you'll find that usually only a small amount of rudder is going to be required.
Now that we know how to counter the slipstream effect in both pitch and in yaw, let us consider how to enter a climb in the Cessna. Transitioning from level flight to climb involves pitching up. So let us first recall that an aircraft in level flight, we have a balance of forces as we've covered in our previous lesson on straight and level flight. As the nose points up, the balance of forces changes. Lift, drag and power follows the climbing path of the aircraft, whereas weight does not. This means that some of the propeller thrust is now acting opposite of the force of gravity. This vertical component of power is working to pull the aircraft to a higher altitude. Lift and power are now acting together to counter the weight of the airplane and to pull it to a higher altitude. However, since some of the weight is now acting afterwards in the same direction as the drag, we find that the airspeed starts to decay. This is undesirable as we aim to fly at a certain specific climb speed. We can stop this trend by increasing our power. And to achieve our maximum climb performance, we would want to maximize our power output. On most general aviation planes, climbing is usually done at full power and at fixed predetermined speeds, as this allows us to achieve the maximum climb performance. But just how much should we raise the nose? And what airspeed are we looking for in a climb? To understand this, we need to be aware of our first V-speed, and this speed is called Vy. Vy is the base rate of climb speed. This is the speed that, if flown, will give us the maximum altitude gained per unit of time. It means that flying at Vy, we'll reach our desired altitude in the minimum amount of time. This is usually the desired option over the other one, which is climbing at Vx. Vx is the airspeed that gives us our best angle of climb, and this means we would achieve the largest gain of altitude per unit of distance traveled. This means climbing for a longer time, but using a less distance to achieve a certain altitude. Climbing at Vx would be beneficial when trying to climb over obstacles, and this is something we'll cover at a later stage. For now, we'll focus on Vy, which is the desirable option in most other cases, where reaching our cruising altitude in the least amount of time is best. On the Cessna, Vy is about 75 knots, and Vx is about 65 knots. These figures differ somewhat depending on aircraft status and environmental factors, but memorizing these easy-to-remember figures is good enough for everyday operations. Note that you can also see the exact airspeeds on the airspeed indicator, as shown here. But as Jason will soon tell you, your main focus should always be to find the nose attitudes that correspond to each airspeed. So try not to get stuck staring at your instruments.
Now let us see how to perform a climb at Vy. Here we are in level flight. As we prepare to enter our climb, let's find the landmark straight ahead again. Keep your eyes fixed on it. We're going to go ahead and smoothly add some power and simultaneously add that right rudder input. Let's raise our nose to right about here. See how the nose cowling rests just on top of the far horizon like this? This is our approximate VY climb position. As airspeed starts decaying from cruise speed to VY, we are going to lose some of our elevator effectiveness. Less airflow over the stabilizer means less aerodynamic force. This means we'll have to add more nose-up control input to keep our pitch fixed at the climb attitude. We use trim to neutralize this control input, keeping our pitch attitude stable. This allows us to have a light touch on our control device at all times. When we feel the aircraft being stable and trimmed, glance down on our instruments here. Our main instrument is our airspeed indicator. Great news, we're at 75 knots and climbing at VY. Great job there. As you can see, our altitude is increasing at a steady rate. Now, as always, we want to be eyes outside as much as possible. Having now confirmed that we're flying at VY, look back outside, focusing on maintaining our pitch attitude here. Now we can settle into the climb and really take in all the views. Climbs involve transitioning from one altitude to another altitude. So at some point, we're going to have to start considering leveling off. If we're climbing to a much higher altitude, this is a concern a few minutes into the future. When we are in their intermediate climb, there's no need to scan the altimeter more than occasionally. But as we approach the desired altitude, we begin to take greater interest in our altitude. As we approach our altitude, judge when to start leveling out. About 50 feet of your target altitude is a good reference. When it's time to level off, look outside, not on our instruments. Slowly start reducing that pitch attitude to regain level pitch attitude here. Maintain the level flight attitude and full power. Trim if you need to. Check your airspeed. Once it's close to the cruise speed, prepare to reduce the power. Look outside and find a landmark straight ahead. Reduce power and maintain level pitch attitude. Reduce that right rudder input to maintain yaw. Use pitch trim as necessary to neutralize the pitch input. Check if your RPM matches the cruise power intended. If not, just make small adjustments and retrim if necessary for stable level flight. Wonderful. We're now back at level flight again at our new altitude.
Great stuff. Let's now introduce climbing turns as well. Turning while climbing is slightly different from turning in level flight. First of all, climbing turns are made at 20 degrees off bank instead of the usual 30 degrees off bank. And the reason for this lower bank angle is primarily performance. Let me explain how. You may remember from our previous lesson on turns in level flight that banking requires more lift to be extracted by the wings. This in order to maintain a constant vertical lift force. And this is usually achieved by increasing our angle of attack. Increasing the total lift extracted by the wings also generates more lift-induced drag. And this extra drag causes a decay in airspeed. But in a climb, as shown here, we want to fly at a specific airspeed, and this airspeed is usually VY or 75 knots. And to make sure we maintain VY, we'll have to lower our nose before we initiate our bank angle. As we start banking, our lowered nose attitude will allow us to maintain our airspeed at VY. This reduction in nose attitude will incur a loss of climb speed. That means in a climbing turn, we're essentially trading climb rate for turn rate. If we banked excessively in our climb, we'd suffer a greatly reduced climb rate. And a bank angle of 20 degrees is a good compromise between lost climb rate and turn rate. The entry into a climbing turn needs to consider another important factor, and that is the slipstream effect. The slipstream effect will either add or subtract from the adverse yaw effect caused by the ailerons, which is a phenomenon we discussed in our earlier lessons. Since the slipstream effect at full power causes the plane to yaw to the left, thus requiring a right rudder input, we'd find that we need even more right rudder when entering right climbing turns. Inversely, when entering left climbing turns, we'll find that we require a very small amount of left rudder input. And if the slipstream effect is very large, we may find ourselves even pushing some right rudder instead.
All right, here's how climbing turn entries look in the plane. Let us consider a right turn first. Here we are in steady and trim climb at VY. First, as with all turns, let's look to the right and ensure there's no traffic. Then we're going to return our gaze forwards. As we prepare to enter the turn, we have to reduce our pitch attitude slightly, like this. Let's initiate our turn entry. As we add right aileron, push more right rudder. Right turns are going to require more right rudder than usual due to the combined reaction of the slipstream effect and the adverse yaw effect. As we hit 20 degrees, reduce aileron and rudder inputs. Because of the slipstream effect, some right rudder may be required here. Note how the 20-degree bank angle appears visually. Take specific notice of the nose cowling position and its relation to the horizon. We can now check our instruments to make sure that the bank angle is correct and that our slip indicator is centered. Cool, let us now consider left turns as well. Let me regain straight level climb. Okay, here we are. We're ready. Let's look to the left. No traffic. Again, look straight ahead. We're going to reduce our pitch slightly. We enter our left turn. Less left rudder is usually required since we're already compensating for that slipstream yaw effect. This is about 20-degree bank angle to the left. Take note of the nose cowling and the horizon position. Let's check our instruments for bank angle and side slip indicator positions. It looks great.
Great job. We've now covered climbing turns. But what comes up must also come down. So now let's move on to descents. There's two main ways to descend. Power on descent, performed at a positive power setting, and power off descents, performed at an idle power, or with the engine failed. So let us first consider power on descents. Here is an aircraft in level flight. Power on descents are performed by reducing the power slightly from the cruise setting. And as we do this, we'll let the aircraft's nose slightly lower, aiming to achieve the same airspeed as we had in level flight. Doing this, the plane will now initiate a shallow descent. Looking at the balance of forces, we can now see that some of the airspeed is achieved by the forward-acting component of weight. We are now spending potential energy, which is altitude, to maintain forward speed. This power-on descent mode is favored as it provides a shallow descent while maintaining a high forward speed, ensuring we get where we want to go in an efficient and timely manner. It also prevents the engine from being cooled too rapidly, which could increase engine wear and tear. Also, when we maintain the same forward speed as in level flight, planning is eased, as we'll fly a consistent forward speeds in both cruise and in descent. Theoretically, we could do a power-off descent at any power setting of our choice. The more we reduce our power, the more we'd have to lower our nose, and the higher our vertical speed would be, assuming that we maintain the same forward speed. However, a good vertical speed target for everyday operations is around 500 feet per minute. This is an easy to remember figure, which can later be used by us to plan our descents into new airports. It also ensures that the power is high enough to prevent the shock cooling and wear and tear to the aircraft engine that I spoke about before.
Let's do a power-on descent in the Cessna now. Here we are in level flight again. We're cruising along at 5,500 feet. Our plan is going to be to descend to 2,500 feet. Following the target that Martin just gave us, we'll need a vertical speed of about 500 feet per minute. We're looking at a few minutes descent to get down there. We know from our experience with the Cessna that a power setting of around 2,000 RPM is good for a 500 foot per minute descent. And basically, that'll give us cruise speed, which is basically just shy of 95 knots at this altitude. As we prepare to reduce power and enter our descent, Look straight ahead, finding a landmark. Let's reduce our power slightly. The reduced slipstream effect causes our nose to drop slightly. I will assist as required to put the nose about this distance from the horizon. As you can see, the pitch attitude is slightly lower than our level flight pitch attitude. Use trim to be stable at this pitch attitude. Now, check our instruments. We're interested in our vertical speed and our airspeed. As you can see, our vertical speed is about 500 feet per minute, and our airspeed is just below 95 knots. Great work here. Let us now consider what we would do if our values were a bit off. First, if our vertical speed and our airspeed is too high, we're now flying with too low pitch. The aircraft has accelerated, and the lower pitch makes us descend quicker. In this scenario, simply reduce pitch attitude. Inversely, if we have too low vertical speed and too low airspeed, our nose attitude might be too high. If this happens, we're going to lower the pitch attitude. More interesting is what we do if we see this scenario. Here we have the proper airspeed, but too high vertical feet per minute. Can you guess the issue? In this scenario, our power setting is too low. We've been forced to lower the nose more than we wanted, thus maintaining speed, but at the expense of a higher vertical speed. In some scenarios, we do this to descend quicker, but in this instance, we like to correct to get back to normal descent rate. Again, let's check our RPM indicator and increase power to 2000 RPM. We raise the nose slightly back to our known power on descent pitch attitude. Voila, our vertical speed comes back to 500 feet per minute. Let us now consider the transition from descent to cruise. Approaching our level off altitude, I slowly add power and meet with some left rudder. Remember, we only need to add a little bit of power to reach 2300 RPM, our cruising power. Only a touch of rudder is necessary here. We make sure that our nose attitude is back in the level flight position and retrim is necessary. We've now reached our new altitude.
The last maneuver to cover today is the power off descent. And in this descent mode, we are descending with the engine power all the way back to idle. Flying with the power at idle, we can see that the balance of forces now only involves three vectors: the lift, the drag, and the weight of the aircraft. Since power is removed, we must use some of our potential energy, that is our altitude, to ensure that we maintain a forward airspeed. Thus our weight, and in extension the force of gravity, is used to maintain the forward speed. This state is almost the same as what would be present after an engine failure. And due to this, we always fly power off descents the same way we would fly following an engine failure. Power off descents are flown at an airspeed that corresponds to the best gliding range. And this airspeed is a fixed value for each aircraft, and for the Cessna in particular, it is 68 knots. This corresponds to the airspeed where we achieve the most lift compared to drag, which means the lift divided by drag is at its highest value. The reason for flying at this particular airspeed is simple. Flying with the most lift compared to drag ensures we can glide the maximum distance. Lift allows us to stay airborne for a long time, and minimizing drag ensures we can glide the best range during that time. Following an engine failure, it is vital to ensure we can maximize our chances of making a good off-field emergency landing. And flying at any other speed, both higher and lower than the 68 knots, will reduce the distance we cover with the engine power at idle. We'll cover emergency power-off landings later, but for now, simply keep in mind the reasons why we are flying at the best glide speed when doing power-off descents. And that is, we want to ensure the maximum range in case of an engine failure. If we always practice our power-off descents this way, you will become very good at handling engine failures if and when they occur. And again, the best glide speed for the Cessna is 68 knots.
Let's see how power-off descents are entered. To enter a power-off descent, first look straight ahead, find your landmark, and reduce power smoothly to idle. As you do, you'll find the reducing slipstream effect forces a left rudder input. The nose is going to want to drop as soon as we reduce power. Our goal is to resist the pitch down moment. Use this pitch angle, which sits close to level flight attitude. This effort requires a lot of initial nose up pitch input. Make sure you use your trim. It's there to help you. As airspeed decays towards 68 knots, more and more trim is required to maintain pitch, as the elevator effectiveness is reduced with reducing airspeed. Once the airspeed is stabilized at 68 knots, the aircraft will be in a shallow descent, flying at the best lift over drag speed, or the airspeed for best glide. We're in a power-off descent now. If the airspeed becomes too high, we need to raise our pitch attitude slightly. If the airspeed becomes too low, we're going to have to lower our pitch attitude slightly. As we approach the desired altitude, we must exit our power-off descent in a controlled manner. Remember that we're considerably trimmed nose up. We must now increase our speed back to cruising speed. The safest way to do this is to slowly increase power to full while maintaining level flight pitch attitude. As airspeed increases to cruise speed, I can again reduce to cruise power. Let me show you how it's done. Here we are approaching our target altitude of 20,500 feet. I'm in a power-off descent, trimmed and stable at 68 knots. Just as I'm about to reach 2,500 feet, let's look up. We're going to find a landmark straight ahead. I gently and smoothly apply power all the way to full. Now beware, this will induce a large pitch-up force, as well as a large yawing motion that requires a lot of right rudder. This is due to the sudden increase in slipstream effect. Again, we need to trim as necessary to maintain level flight attitude. Glance down on the airspeed indicator. As the airspeed approaches cruise speed, let's reduce power back down to 2,300 RPM. As we reduce the power, make sure we adjust our pitch control to maintain level flight. Lessen that rudder input as the slipstream effect reduces as well. Finally, trim for level flight. All is well, and we're now stable at 2,500 feet.
Let's move on to the final segment, which is turns in power-off descents. Turns in power-off descents must consider the fact that we're now doing our very best to maintain 68 knots as exactly as we can. And this is the speed that will give us our best gliding range, and it must be flown at all times.
Let me show you how to perform power-off descending turns. Here we are in stable power-off descent at 68 knots, fully trimmed. As we prepare to enter a power-off turn to the right, let's look to the right. Then we're going to return our gaze forward. Let's find a landmark straight ahead. We slightly reduce pitch attitude. As we add right aileron to initiate that roll, we're going to make sure to compensate with enough rudder to maintain coordinated flight. We're going to have to judge about a 30-degree bank visually. Note the nose low position. We check our instruments to verify we have 30 degrees of bank and our airspeed is stable about 68 knots. Remember, the airspeed is very important here, considering we may have an engine failure and want to glide as far as possible. Let me also show you a left turn. We check our left, look straight ahead. Again, there's our landmark. We will reduce our pitch slightly. We start adding that left aileron and simultaneously applying that left rudder. We estimate this is about 30 degrees here. Again, we're stabilized. Now's a good time to check our instruments. Good airspeed, good bank angle. I really look forward to seeing you try this out in the aircraft. Don't worry if it seems like a lot right now. We'll take each maneuver one by one, starting with the climbs. You'll find it easier than you think. It's all about looking outside, flying your nose attitudes, and using your rudder to maintain headings toward landmarks. You've got this. As always, we'll see you at the Academy website, where you'll find more preparatory material as well as an easy way to access the training sessions for use inside Microsoft Flight Simulator. Also, please feel free to leave a like and subscribe to us, and drop us a comment. That way, you can help us keep creating more educational content right here on YouTube. We'll see you in the plane.